and I am part of the Spacecraft thermal management systems, and I'm one of the sub-leads. I'm currently responsible for the software lead.
My name is Sir Vasquez, and I'm the hardware team.
And I'm Janet Hinkle, and I'm in charge of the variable emissive device.
And we're working with Dr. Khalil Rafiki and Professor John LaRue, and designing a radiator for our CubeSat. A little background about our project. We're basically trying to have temperature control for the two-unit CubeSat that is supposed to be in low Earth orbit. Our current spacecraft use multiple types of thermal control, such as for active, there's resistive electrical heaters, and then and there's also heat pipes or fluid circulation. For passive, there's the multi-layer insulation, mirrors and reflectors, and what we're using is thermal coaters. And then we'll talk more about that in a few. So our goals for this project, in terms of software-wise, was to be able to use COMSOL or ANSYS Fluent to be able to create a model of the radiator and analyze the thermal loads on that radiator. And after we've done that, we would correlate the data we get from the software to the data we obtained from the tests we did at Boeing, and see how our software reflects with the actual experiment. We also used Satellite Toolkit, also known as STK, to help model the two-unit CubeSat in polar low Earth orbit. And from there, we were able to estimate the radiator temperature on each side of the CubeSat to be able to help us give us a little feeling of what's going to happen when it's in the space environment. And then for hardware.
So the goals for the hardware team were to calibrate the measurement instruments that we use to measure the temperatures of the plate, as well as troubleshooting and then just maintaining the vacuum chamber that we'll be using for our tests.
And as far as the variable emissive team, our goal was to create a film that we can measure the emissivity of, and then as well as find a way to test the functionality of that film that we created.
So a little overview of what we're going to go over. For software-wise, I'm going to show you some things we've done in ANSYS and COMSOL regarding thermal modeling, and I'm also going to show you what we've done in the STK software. For hardware, we're going to show you some sensors and calibration and vacuum chamber testing, and for chemical, we'll demonstrate the chemical film we've developed. So for software-wise, we first started out with COMSOL, and we tried to model our radiator in COMSOL since the beginning of this year, in the fall. However, we've come across some difficulties in trying to get a solution to converge. And we've been going back and forth, and trying to be able to solve what's going on and why our model is kind of failing in terms of solving the simulation. In that case, I took the route of going into using the ANSYS software and see maybe if that can help us help us out and work with something, getting a solution. And I was able to model it from scratch, and thankfully it worked right there on the spot. So here we see demonstrated the cold case, so when the CubeSat is not facing the sun, and we have the hot case when the sun's actually when the CubeSat is facing the sun. So when you have heat applied to it, and pretty much when it's on the cold side, no heat applied. From that, we were able to grab some data from the software and correlate that with the data from the Boeing test. And we went ahead and graphed the data from Boeing, and we saw three points for upper cold and 2 major points for hot. And from that, we were able to correlate ANSYS and Boeing, and we saw that there was a difference of 0.25 to 0.27 from the fluid model, and a 0.20 to 0.22 difference in temperature from the Boeing. And therefore, we agreed that the data is mostly agreeable, and that we can hopefully move on and be able to model this in an actual space environment. STK-wise, system toolkit modeling, we simulated our two-unit CubeSat in 300-kilometer orbital altitude, and we used a Blender program that integrates the SolidWorks model, and where you can apply sensors to be able to measure the thermal load on each side of the CubeSat. And we were able to determine, as you can see from the graph, that the maximum total thermal load was 11.928 watts. where the extra 3 watts is from the heater itself, heater produced power. And I'll hand it over to hardware. We'll talk about their contribution.
So the sensors we used in our previous test plate that was tested at Boeing were thermocouples. Those are these black wires here. And so what we went ahead and did was we calibrated the thermocouples. So what we basically did is using a DAC, measured the temperature of ice and boiling water, which we know should be 100 degrees Celsius and 0 degrees Celsius. And so we compared that with the PRT, which is pretty much just a very precise thermometer. And we got that our results were within plus or minus 1 degree Celsius, which is the industry standard. And so for our next test plate, we will be using a new sensor, which is pictured up right there. And so the major benefit of this new sensor is that the analysis is much simpler. So instead of a quadratic relationship between temperature and voltage, it's linear. So it'll be much quicker and simpler to analyze the voltages given off. And so in our next test plate, we're going to actually use both and then compare the data. So like I said, we're going to be doing a minimal vacuum chamber test. So this is the new plate. It's right here, that's the bottom side. And so the major improvements between the new plate and the old one is how we're heating it up. So for this new one, we're using a heating strip instead of the previous one. So the heaters in the previous one were these little rectangles right here, and then they were wrapped with wires, and then a voltage was applied. And so it's pretty much the same concept with the heating strip, but it's just more precise. And we're also using the new sensor, like I said. And so we're going to be doing this test in the vacuum chamber that we've been troubleshooting sometime next week around Monday-ish in Professor Camaro's lab. Yeah, so that's it for hardware.
And now for the chemical aspect. So essentially, me and my team, chemical engineers, we tried to create this film, variable emissive film, in which you apply voltage and then it'll change the emissivity of that film, which would be great for in space applications. When you're facing the sun, you can reduce the emissivity and then reduce the intake of that energy that the sun's giving off. And then when you're facing away, you can flip the switch and then increase rejection. And essentially up here, as you see, you have the layout of the cell and cross section, and then essentially the voltage will be going through this, and then the lithium ions will intercalate into the titanium dioxide layer, which is the electrical arc material that we've been experimenting with. We've also looked into tungsten oxide, which has been more thoroughly researched than titanium dioxide. So we will be looking at that next quarter, if anything. And as you can see down here, there's various ways that we can test, that we tested to see if our design worked, and how our fabrication process proceeded. By first optical, which you can see here, you can see before electrical loading and then after. Though this test was kind of inconclusive because we weren't sure whether this was actually changing its emissive properties or if we were just burning the thing. So essentially moved on to thermal testing. And if anything here, we tried to isolate the system from basically the ambient environment around it, so we can just see how the cell, the surface temperature of the cell will change as we input and as we put voltage in and then remove that voltage later as well. This has been fairly difficult because the IR sensor that the IR gun that we use to measure this has a specific emissive rating of 0.95. So we recently bought this one, which can give a more accurate and also as well as a visual analysis of what our film is doing when we apply and unapply that voltage. And then as per what we're going to do in the future next year, software team is going to be looking into optimizing orbits. The hardware team will further look into the vacuum chamber testing, especially with this new sensor that we have, and we'll be looking forward to testing that. And as for chemical, we'll be continuing our tests, especially with this new IR sensor, as well as looking into other fabrication processes. And in this case, it'd be sputter coating instead of the manual manufacturing of it that we are doing by hand. And hopefully by maybe winter spring quarter, we'll be able to do actual vacuum testing on an actual on the plate itself, and then see how that works. Thank you very much.